Welcome to the basic experiment part 2. Today we're going to talk about what happens when you have one independent variable that has more than two levels, or when you have more than one independent variable. So far we've talked about different kinds of data, different kinds of experimental design, so between subjects, within subjects, quasi-experimental. We've talked about different kinds of data analysis. Today we're going to talk about what happens when you have an independent variable with more than two levels, right? So up until this point, our independent variables have been two-level independent variables. In other words, there's two groups, an experimental group and a control group. But sometimes you may find that you're interested in more than two groups, two levels of an independent variable. We'll talk about factorial designs. This is when you have more than one independent variable. We'll talk about interaction effects, and then we'll get into a real experiment. So recall the caffeine example. So we're interested in this hypothesis that caffeine improves mental function. And in the original example, we had one independent variable with two levels or two groups, right? The experimental group and the control group. We randomly assigned people to one of each of these two groups. And again, remember we talked about how we kept the groups as equal as possible except for that independent variable. And then we measure that outcome of intelligence. And we're asking the question, are the two groups different, right? And we do an independent samples t-test because we have two groups, and the question we're asking is, are they different? Now, maybe we think that caffeine does actually increase intelligence. We might ask the question, does the dosage matter, right? Will a higher dose have a stronger effect? So before we had these two levels, we could add a third level, right? We could add a third experimental condition. And now we have an independent variable that has three levels. Now, let's say we go through and we find these means for each of these groups, right? Now when we have this, we have to do multiple comparisons, right? Because now what we need to know isn't just like, is group A different from group B? Is the experimental group different from the control group? But we need to know which of these groups are different from each other, right? So we have to compare this group. We have to compare this group. And we have to compare these groups, right? So when we're doing, when we do an experiment that has more than two levels, three or more, right? We have to do multiple comparisons across all of these groups. When we have more than two levels, so if your senior thesis data has an independent variable with more than two levels, the analysis, the tool, the statistical tool that we use to answer this question is what we call an ANOVA. First, we test if there's an overall effect. So the first test in this kind of analysis strategy is to ask the question, is there a difference between any of these groups at all? And that is our F test. And this is what this looks like in SPSS output. So we're looking here at this F statistics. So we've got caffeine level here, let's see, caffeine level here, and then we've got our F statistic here, 7.68, and then our p-value, 0.001. And this is a statistically significant effect. Remember earlier in the course when I said I could totally just make up data to show what I want? I just made up this data. All right, this is a statistically significant effect. P is less than 0.05. So once you've determined that there is at least one significant difference between your groups, then you have to do additional tests to test for significant differences between the levels of these different groups. We talk about these as pairwise comparisons. So here we're going to compare the no caffeine group to the 100 milligram group. And we look over here for the significance value, and is that less than 0.05? It is. And the no caffeine group to the 200 milligram group, and that is significant as well, 0.001. So the people in the 100 milligram group and the 200 milligram group scored significantly higher than the people in the no caffeine group. Now, the next comparison we want to make is a comparison between the 100 milligram and the 200 milligram group. 100 milligram here, 200 milligram here, and we scroll over. Is that statistically significant? It is not, right? Because 393 is greater than 0.50, right? Or 0.393 is greater than 0.050. So that is not statistically significant. So from this study, we would conclude that there is a significant difference in caffeine versus none, but the dosage from 100 to 200 doesn't really matter very much. And if you end up with this kind of data in your senior thesis, like this is the kind of analysis that you would expect to be able to perform. The reporting of this, so we start with the omnibus test, this F test. There's a significant effect of caffeine consumption on intelligence. And then we give the F, the degrees of freedom within and between. And that goes from there and there. We get the F, and then we get the p-value. Typically, we give p is equal to 0.001. Sometimes when the probability is very, very, very low, so that p-value will register on SPSS as 0.000. It's not actually 0, it's just very, very tiny. So in that case, then we would report less than 0.001. And then we go through and we add back in the means for each of these groups, and we talk about who scored higher than whose. So they're the people who got the 200 milligram scored higher than the 100 milligram. The people who got 200 milligrams scored higher than the control. The people who got 100 milligrams scored higher than the control, and there was no significant difference between the 100 milligram and 200 milligram groups. Now, there are times when we want to manipulate more than one independent variable, right? So, for example, we had talked about in class how sleep might affect how well someone does on this intelligence test. And so we could ask the question, what if in addition to the effects of caffeine, we added in an independent variable for sleep, right? So we brought people into our lab, and some of them we let them sleep for 8 hours, and some of them we only let them sleep for 4 hours. And when they wake up, we randomly assign them to either get 100 milligrams of caffeine and then no caffeine, and then we measure that dependent variable of intelligence. So now what we end up with is a participant can be randomly assigned to 4 possible conditions, right? Because there are 4 possible combinations of these independent variables, right? So you can either be in the 100 milligram and 4 hours, 100 milligram and 8 hours, or the the no caffeine group and 4 or 8 hours. And so we would call this a 2x2 factorial design because there are 2 levels of each of these independent variables, right? 100 milligram and none, 4 hours and 8 hours. And when you multiply 2 times 2, that gets us 4 possible conditions. Now, using the previous example, what if we wanted to have that 3-level independent variable? So if we kept that 200 milligram condition from before, this becomes what we call a 3x2 factorial design, because we have one independent variable that has 3 levels, one independent variable that has 2 levels, and 3 times 2 is, that's right, 6. And so that means there are 6 possible conditions that a person could be randomly assigned into, right? Or you can think about this as there are now 6 groups. One group of people gets 4 and 200, one group of people gets 8 and 200, so there are 6 possible groups, okay? Now, what's cool about factorial designs is that they allow us to test hypotheses about 2 independent variables in the same study. And so that's neat because we can look at these main effects of each independent variable on the dependent variable while controlling for the other level. So does caffeine lead to an increased intelligence controlling for sleep? Does sleep lead to an increased intelligence controlling for caffeine? And when I say controlling for sleep or controlling for caffeine, what I mean is if I do a comparison of the sleep conditions, let's say, so 4 hours and 8 hours. So all of the people in the 4-hour group, all of the people in the 8-hour group. Well, in this example here, in the 3x2, for the people in the 4-hour group, some of them are in the 200 milligrams, some of them are in 100, and some of them are in none. And when we do our comparison of just this group to this group, 4 to 8 hours, then what we're doing is we're controlling for this. That means we have equal numbers of people in all of these different groups, and so we're controlling for the effects of caffeine, right? Because the same thing is true in the 8-hour group. They have the same distribution of people in this caffeine group. So when we look at just one independent variable at a time, we're controlling for the other independent variables in the design, and we call this a main effect. But what's also neat is we may also be interested in combinations of variables, right? So perhaps caffeine has the strongest effects on intelligence when someone has 8 hours of sleep compared to 4. And when we look at this, now we're looking at an interaction effect. And an interaction effect is when we make a prediction or we're concerned with one of those particular categories, right? So now we're not just looking at the difference between the 4 hours and the 8 hours, the difference between the 200 milligram, 100 milligram, and none. We're looking at one particular cell, right? 8 hours and 200 milligrams compared to these other 6 cells. Okay. Now, the way to think about an interaction is that it's the effect of one independent variable that differs depending on another independent variable. So we might say that caffeine improves intelligence, especially when someone has gotten a full night's sleep. And that especially when language, or that only if language. Caffeine improves intelligence only if someone has gotten a full night's sleep. When we use that kind of language, we're making an interaction prediction, and we're talking about sleep as a moderator of the effects of caffeine. So there are some variables that act as moderators in relationships. So the effect of X on Y gets turned up or turned down by Z, by some moderator. Thus far we've talked about hypotheses about main effects, right? The caffeine group scores significantly higher on intelligence compared to the no caffeine group. People will take longer to pull out of a parking spot when someone is waiting compared to not waiting. But when we make interaction hypotheses, we use qualifying language to include the effects of this other independent variable. People will take longer to pull out of a parking spot, especially when someone honks at them, right? And so now that honking variable, whether or not someone honks or does not honk, now that's a moderator. That moderates the effect of waiting, right? So when we use this sort of especially when only if, then we're making interaction hypotheses. And we're usually making a prediction about one particular cell. So I'm going to go through and we're going to talk about what main effects kind of look like and what interaction, a couple different kinds of interaction effects might look like. So when you have a main effect of caffeine and no effect of sleep, we might have some means that look like this, right? So in the 100 milligram group, they got 110 in both the 4 and 8 hours, and in the no caffeine group, they got 100 in both the 4 and 8 hours. So when we graph this out, and graphs are usually the best way to sort of look at main effects and interactions, right? We can see that there's an effect of caffeine, right? People score higher when they get the caffeine, lower when they don't, and there really is no difference here in the level of sleep. So this is a main effect of caffeine and no effect of sleep. Now we could make this the opposite, right? Maybe we could make it so that you do the best when you get 8 hours of sleep regardless of how much caffeine you get, right? So now this is a main effect of sleep and no effect of caffeine. So here you score the highest in the 8-hour group regardless of whether you get no caffeine or 100 milligram, and you score the lowest in the 4-hour group, again regardless if you get the no caffeine or 100 milligrams. Now an interaction effect is when one of these particular cells is significantly different from some of these other cells, right? So when we have, we might predict that the people in the caffeine group are going to score significantly higher compared to no caffeine group, especially when someone has gotten 8 full hours of sleep compared to 4. And now what we're predicting is that there's going to be a main effect of caffeine, right? Caffeine's going to affect people's scores on intelligence, but the level of sleep you get is going to turn up that effect, right? It's going to make it stronger, right? It's going to moderate that effect. And so this would look something like this, right? So the interaction is here. The interaction is here, and the difference between the 4 and 8 hours within this one cell here. If this is significantly different, then we would have a statistically significant interaction term, right? So the people who got 8 hours of sleep scored significantly higher than the people who got 4 hours of sleep within that 100 milligram condition, right? And that's what makes this an interaction, right? There's a significant difference within this condition. Now, comparing this to the no caffeine group, there's also probably a main effect of caffeine, right? So if we collapse these 4 and 8 hours together, in other words, if instead of breaking these apart, we just look at this one group compared to this one group, I'd be willing to bet that there's also a main effect of caffeine here, right? Where the people in the 100 milligram group scored higher than those who in the no caffeine group, regardless of how much sleep they got. So we're going to talk for the last time about that study that I did on explicit prejudice. Recall that we had that independent variable of people participating in a study either at home or over the internet. And so that's our dichotomous categorical independent variable with 2 levels. But I might also be interested in participant ethnicity, right? Maybe I think that this effect of explicit prejudice expression might be strongest for non-whites or whites when they're on campus or off campus, right? So I might have an interaction hypothesis. So what I can do is I can look at the effect of whether you're at home or on DePaul's campus, and whether you are white or non-white, black and Latino, and we can look and see if that has, if there's any interaction effect in predicting explicit prejudice. Now, by the way, I only did this for the sake of class, and I'm not really sure what the pattern of results means, but you could make a prediction, right? You might predict that the white participants are going to express significantly more explicit prejudice when they're off campus compared to on campus, and that will be significantly higher than the non-whites. Or in other words, there will be effect of the location on expression of explicit prejudice, especially when the participant is white, right? That would be kind of an interaction hypothesis. As it turns out, the results are completely different from that. So when we look at this, this is again an ANOVA. ANOVA is cool because it can handle more than one independent variable. It can also handle independent variables with more than 2 levels. So notice here in this same between subjects effects table, we've got our main effects for our independent variables, so lab versus internet, non-whites versus whites. And then down here we have our interaction effect, which if you want to be nerdy about it is literally like just the multiplication of these 2 variables. Your score here times your score there is the interaction effect. So when we look at this, is there a significant main effect for lab versus internet? No, right? 0.418, not significant. Is there a significant effect of whites versus non-whites? Again, no, there is no significant difference, right? So whites didn't score significantly higher than non-whites. People on the internet didn't score significantly higher than people in the lab, right, on this explicit prejudice. But when we look down here at the interaction effect, this interaction term, this is statistically significant, 0.033. So there is some significant interaction here among these conditions. Now, in order to unpack this interaction, we have to create a graph, right? So in the ANOVA output, it'll give you estimates of the means for each of these groups. So this is the internet group, non-whites and whites, lab group, non-whites and whites. Here's the means for each of these groups, which I've just plotted down here. Now, what's kind of unusual about this data, right? There's some things that make sense, right? So the people who are scoring highest on explicit prejudice are the whites when they are in the internet. The people who are scoring lowest on explicit prejudice are the non-whites when they are on the internet, which again makes sense. But what's interesting about this data is that when the people come into the lab, their expression of explicit prejudice changes a little bit. So the non-whites increase a little bit, and the whites decrease a little bit, which is really weird. Like, I'm not really sure why this is. this could be like a real pattern. So it could be that perhaps non-whites, when they're in a university setting, especially like at DePaul University, which tends to be sort of a more skews more a higher socioeconomic status. It could be that there's sort of some code switching where non-whites sort of feel like to fit in they have to be slightly more prejudiced or something like this. Again, we're looking at these numbers at the very bottom end of the prejudice scale, so it's not like they're coming out and being like, I hate black people. It's just, there's slightly more. It could be more of a homogenization of attitudes that we see when we're on campus versus off campus. I'm not entirely sure why. Or it could be a type 1 error, right? This could be just something that's statistically significant by random chance, and if I did this again, it wouldn't come out this way. It wouldn't be significant. So it's hard to know. Point is, when we do this, we want to look at this pattern and see what the pattern looks like, and then we need to do direct comparisons. So, and when we do these direct comparisons, just like we did with the 3-level independent variable, we ultimately end up needing to compare each of these groups together. So we compare the non-whites in the internet compared to the whites in the internet, non-whites in the internet compared to non-whites in the lab, non-whites in the internet compared to whites in the lab, right? We do each of these comparisons. And here we see that for the non-whites, it seems like there's a marginally significant difference here between this 1.76 and this 2.13. And I'd be willing to bet what's driving this interaction, I don't have this table for you, but is this difference here between the whites and non-whites on the internet. So that is it for the factorial designs and the more than one independent variable. Hopefully that'll be very helpful for you for the quiz for this week. Also, hopefully that will be helpful for you for your senior thesis if you end up with this kind of design where you have more than one independent variable, or if you're making an interaction prediction, or if you have multiple levels of your independent variable. As always, shoot me an email if you have any questions.